All right, if you can
We're back again.
We're back again, technical difficulties. If you can hear us, please put a thumbs up or a yes in the comments, and then we'll know that our sound is working. So if there's anyone watching who can tell us that we're working all right, go ahead and give us a thumbs up.
Are you hearing us out there in the wide world?
No, no sounds. Can everybody hear us? Is the blue thing going when I talk, Lilit? Yes. Okay, maybe we just don't have any watchers yet.
Okay.
All right, well, we're gonna start heading into the Mars yard. So, so Charles Cockle, please tell us why as we walk through, please tell us why we're down in a mine as an analog to Mars.
Yeah, so welcome everyone. We're down here in the Boulby mine, kilometer underground, and we're testing out technology for the robotic and human exploration of Mars. And we're using the mine because it's an underground environment that can tell us something about the exploration, say, of lava tubes or caves on other planets. But also, it's an extreme environment where we're interested in looking at life and ancient signatures of life in these salts. We're actually standing here in 250 million-year-old salts in this mine. So we've got over 30 people here from Europe, from the US, from Asia, many other places, testing different bits of technology, drills, life detection equipment, and other instruments that will one day go to Mars, including some that will go on the ExoMars European rover. This is a laboratory and a mine with over 1,000 kilometers. It's a facility run by the Science and Technologies Facilities Council here in the UK. It's a very impressive facility, and you'll be seeing some of the other things that go on here, not just Mars exploration, but the search for dark matter as well. So let's have a wander over and show you the Mars yard, where we're testing some of the instruments that will one day go to other planets. So we're walking away from the lab now. As I say, we're a kilometer underground. This mine was started in the 1970s. It's been around for 40 years. And we started building an astrobiology lab here about 4 years ago. And right behind me on my right here, you can see a small miniature lab, an outdoor lab that's internet connected and has air conditioning. And we're now walking into the Mars yard where we can test out rovers and other technology. You can see some nice samples here, 250 million-year-old salt that some of the scientists are beginning to test to look for signatures of life, to look at the geology and geochemistry. And then out here in front of us is the group from Luleå, and they're going to tell you about some of their instruments. So maybe we will...
Yeah, so here we have the Luleå University group who has some very impressive instruments that they're going to show us. So we have some researchers and engineers, and they're going to highlight what they're doing down here in the Mars yard. So please go ahead and introduce yourself and your team.
Thank you, Audra. So this is Tashwin Manandlal from Luleå University of Technology. So I'm a PhD student with the Atmospheric Science Group, Luleå University of Technology, Sweden, working with Professor Javier Martin Torres and Professor Maria Paz Zorzano, who are the primary investigator of the instrument HABIT. And now I would like to introduce my team, who is also here. He is Miracle Israel. He is also a PhD student from Tamil Nadu, India, and he's working on an instrument which he will be later explaining after me. And we have Dr. Anshuman Bharadwaj. So he's from Uttar Pradesh, India. He is an associate senior lecturer with the Luleå University of Technology, and his main research interest is in glaciology and remote sensing. And here we have Alvaro. He's a PhD student who is in his final years of completion of his PhD, who's working with the HABIT instrument. And now we would like to explain to you with the instruments that we have over here.
Yeah, so please tell us about these instruments that you've set up. Now, our Wi-Fi means you guys can't, unfortunately, you can't come this far, but we can at least highlight what they're doing. So I'll stand to the side while these guys show you what their instruments are.
So here we have HABIT. HABIT is the first Swedish instrument to go to Mars through the ExoMars 2020 rover. And HABIT has been developed by us at Luleå University of Technology. HABIT instrument stands for habitability, brine, irradiation, and temperature. So the concept behind the working of HABIT is deliquescence. Deliquescence is a phenomenon that we observe in our everyday lives. So have you seen on a rainy day when we have a bottle of salts left in open, it becomes quite mushy. This is because of the presence of the moisture in the atmosphere, which is being absorbed by the salt.
Wow.
We use the same concept in HABIT. HABIT has 6 containers, 6 vessels, in which we have hygroscopic salts filled in 4 of those vessels. And these vessels are open, can take in moisture from the atmosphere, and through the changes in conductivity, we find out the amount of water present. And we have 2 open containers, which you can see over there. These containers are to be having the Martian dust to get accumulated to also see its effect with the atmosphere. So this is the concept of HABIT. And this part of HABIT is called bottle. And along with bottle, we also have an environmental monitoring station, which has its heritage from the REMS instrument about the Curiosity rover. So we have an air temperature sensor, which is used to measure the temperature of the air, with which we are also able to determine the wind speed and direction. We also have UV sensors, which are able to measure the UV irradiation in different wavelengths. And we also have a ground temperature sensor facing the ground, which is used to measure the ground temperature. This entire part of HABIT instrument is going to be on the surface platform of the ExoMars 2020 mission.
So just to clarify, the HABIT instrument is all about environmental conditions monitoring.
It's more, yeah, I can come into it.
Yeah.
So HABIT is mainly an instrument that is going to it's going to answer the question of the most important 2 questions that we have on Mars is there water on Mars? Is there life on Mars?
Okay.
So these 2 are very interesting questions that we would like to address. Obviously, when you find water on Mars, the chances of finding life increases.
Right.
And first, to find out water on Mars, we have the bottle instrument, which is going to measure. And the environmental part is just to measure the parameters which are going to affect the working of this part.
I see. And so to look for water, you fill some of the cells with salts, which can absorb water,
salts,
correct?
Which can absorb water.
Right. So if if water is absorbed, the conductivity goes up, which means that there's water in the atmosphere.
And moreover, HABIT is a technological demonstration for in situ resource utilization that water can be obtained from the atmosphere of Mars. This can be useful for future manned missions to Mars, where water is the most important requirement.
Right.
And
so do you think that after you collect the water in the salts, it could possibly be used by the
crew members,
who could be on Mars? Excellent.
And moreover, we are also seeing surface features through high resolution imagery from satellites, which show some features like recurring features which occur, such as the slope streaks and slope lineae. So they have been attributed to the presence of high amount of deliquescence. So using HABIT, we can try to show them, we can try to find out if there is high amount of deliquescence present in the atmosphere.
Wow.
So
why are you testing this instrument underground in a mine?
Yeah, that's a very important question. And as you know, Mars has an extreme environment.
Yeah.
It is, as you find, there's low gravity, there is a fraction of the atmosphere contains oxygen, and we have very low pressures around. So it's an extreme environment. So before we send an instrument to such an extreme environment, we need to make sure about its operation in extreme environments on Earth. So as you would have seen, like the previous NASA Spacebound program, we had HABIT prototype being tested at Ladakh at high altitude, which was a cold, dry, arid region. And we also had tested in Iceland, which is also a cold desert. And now we have it in the mine, 1.1 kilometers below, where we have, as you see, the environment is dry and salty. It's a natural salt mine. And you also have HABIT working with salts. So it is pretty much analogous for testing HABIT in such an environment.
Yeah, excellent. Thank you so much for sharing. And you have another instrument here as well?
We have a next instrument, Metabolt, which Miracle will be explaining more. So I pass on to the mic to him.
Okay. Sure. So please go ahead and introduce yourself. Give us your name one more time.
Thank you, Tashwin. My name is Miracle Israel. I primarily work on an instrument called Metabolt, which is one of the instruments we develop in our lab in Sweden. And it's the first instrument of astrobiological instrument we develop in our university at LLTU. One of the big questions we have, the planetary scientists all over the world have, is if it is successfully observing the biological processes that is happening all over, any place away from Earth, for example, Moon or other planets like Mars. But we have been working on that for more than half a century, but we still haven't found the answer for that. This Metabolt instrument is a step towards that. We have designed the instrument to detect the metabolic activity of the soil and the salts which are contained in the instrument, and then we measure certain parameters that are relevant to that to the metabolic activity happening inside the samples. The first step towards the searching for biological processes on other planets, for example Mars, started when NASA launched the first Viking lander mission in the late 1970s. And that mission had 3 experiments, of which 2 of the results contradicted, and that leaves so many questions in the minds of the scientists still. For clearing that confusion, the NASA again designed an instrument called Mars Oxygen Experiment in the late 1990s, and this experiment came to an end even before launch because of the launch failure.
Oh wow!
So this Metabold instrument we are developing, it includes the existing methodologies which were used in the previous experiments of Viking and the Mars Oxygen missions. Also puts together some more crucial measurements which we found relevant to the metabolic activity.
So when you say metabolic activity, so you're looking at the products of breakdown. So if you can see these products of breaking down sugars or products of metabolism,
yes,
then that means that there's some microbes living in the soil. Is that what you're looking for?
Yeah. So the instrument we conduct, it has 2 containers. In one container we use samples with just water, and in another we have samples with sugar solution, and a number of sensors in the experiment container to over time the variability of those measurements and how the metabolic activity is affecting those measurements.
Is that the purpose of doing that? Excellent. And so why?
The instrument we brought here is the first prototype of Metabold. So we wanted to bring to a Mars analog location with the salts naturally available here in the mine. So we wanted to test, and actually with the experiment, it's going on right now. And the samples we used are from the doorstep outside the laboratory, which showed maximum DNA fingerprints. So we expect to see some metabolic activity from the experiment we conduct now.
Excellent. Great. Thank you so much for sharing. We also have another professor or engineer who's going to show us some of his instrument. I think we're going to walk around the corner. So thank you very much, gentlemen. I'll take your microphone.
Yes. Thank you.
As we walk through. Thank you, guys.
Thank you.
So you guys have seen some great engineering that's going on down here. Some instruments that are going to be used on future missions to Mars. Now I'm going to take you to meet an engineer who's working on an instrument that's going to be on a rover. I'll let you clip that on yourself.
Okay. There we go. Does that work?
That's great. So how are we on lighting? Should we face the other way? Can we turn this way so they can see us? Is that a little better? Okay, so please go ahead and introduce yourself.
Okay.
I'll step back.
Well, hello. My name is John Holt. I'm a research engineer from the University of Leicester, and this is my colleague Jim Campbell, and he's one of our mechanical engineers. He helps to design things to work in the space environment. So we've got an instrument prototype here that we're going to just talk to you a little bit about. So this is SPLIT, a small planetary linear impulse tool. Now, just to give you a little bit of context, if you were to go outside right now even and pick up a rock from the floor, just like this one, and if you were to break it open, you would probably find evidence of microbial life living inside of that rock. You might see some little green layers just below the surface. And they're a type of bacteria that we often call cyanobacteria. Now, for that reason, we don't think it's unreasonable that if there was ever life on Mars, and we don't know if there was or was not, but if there was, maybe that life would have lived inside the rocks as well. So just like a geologist, you want to break open that rock with a hammer and look inside. And that's where this device comes in. So you can imagine we're on the surface of Mars, we've got a rock here, and this device Split applies energy to this tip here so that we can break the rock open. And imagine a sculptor with a hammer and a chisel. This here is the chisel, and the hammer mechanism is inside, applying energy to the rock, and then eventually the rock breaks open. And the rock breaks open because rocks tend to be very brittle, just like glass. If you hit glass many, many times, it will eventually break.
Great. Thank you so much for showing. And so this is a tool that will eventually go to Mars, correct?
Absolutely. We're hoping it does. So at the moment, the European Space Agency have ExoMars going to Mars very soon. And then there will be missions after that, and hopefully we'll be involved in a Mars sample return, and we can use a device just like Split to break open the rocks and then decide which part of the rock we want to bring back to Earth so that we can analyze it, and that'll be really exciting.
Yeah, how exciting. Thank you very much for showing your instrument to us. We're going to move into the clean room now, into the lab. So I'll go ahead and take your microphone. We'll pass this off to Charles, and we'll take you through. So we're now going to walk through the Mars yard back into the lab. So one of the great things about the Boulby mine is that they really support a lot of scientific research, and then they allow this space here to be used as a Mars analog. So now we're going to walk through, and you'll see how the lab is set up. You'll see some of the research that's going on in the lab, meet some of the scientists. We also have a team of educators here. And these educators are working alongside the scientists and engineers. They're learning field methods, they're learning science, they're learning content, and then they're also writing up some lesson plans and activities so that teachers and students can be doing similar things to what the researchers are doing. So here we go into the lab. Okay, we have a couple doors to go through. So at this table here, you'll see we have some educators working. We have Rosalba, who's a researcher, and we have Matthias, who is an astronaut with the European Space Agency. And they're working together to plan an EVA, which is an extravehicular activity that Matthias is going to go on, exploring the use of gloves and bags for sample collection in a Mars environment. So let's take you back. So now we're going into a class 10,000 clean room. So I'm going to pass this off to Charles. Charles is going to show you some instruments while I get changed, because I have to put on some protective clothing to prevent contamination from the dirt out in the mine and from my own cells. So I'm going to get dressed while Charles takes the next.
To things about using this environment to test technology. And the facilities. So down here, we can not only go out and test instruments in the Mars-like environment of the mine, but we can also bring in instruments into this clean lab and test the technology here. So we're going to go and have a look at one instrument, which is a Raman Spectrometer, which can be used to study the composition of salts, to look for biosignatures like organics and other indicators of life, or to understand geochemistry. And like I said earlier, we're in a place with 250 million year old salts. So we're quite interested in finding out what sort of life lives in those salts and what sort of signatures of life are left over. So here we are in the Raman suite. I'm going to hand that to Anu here, and just talk a little bit about this instrument. So Anu, tell us what you've got here. What is this instrument?
Oh,
you want to have a look?
You can come inside. Yeah. So hi everyone. First of all, this is Anushri, and I'm working with Dr. David Wilson here, who's from NASA Ames. So we are working on light detection techniques here. So this is our Raman laser spectrometer. As you can see here, I think the camera is, yeah. Yeah, so this is a very nice Permian halide, and what we do here, when you put this single color light here, what it does is it excites the molecule inside, and the photon which is emitted are transferred into this kind of peaks, and these peaks are very specific for the specific material, I mean sample. So yeah, that's how you detect, and that's how you detect your the composition of your sample.
So Anu, tell me, is the idea that you put this on a rover or take it with human explorers? How versatile is this method?
Yeah. I think the idea that Raman is going to be mounted on the ExoMars rover. So it's very important because it detects, it's a good technique to detect the biosignatures, biomarkers preserved inside the salt crystals on Mars. Yeah. So yeah, that's how it's very useful. And yeah, one more thing that it can also detect the mineral that is induced by water, the geological processes. So it's very good to see the early past or present life preserved in the Martian salts.
So Anu and David here are from the NASA Ames Research Center with this instrument. And one of the things you'll see is that we pass these samples through different instrument methods. So we will drill the salts out like an astronaut on Mars, study them with Raman, investigate them with fluorescence spectroscopy, look for life in them. So all the instrument teams work together here to look at the different types of salts and possible signatures of life. So we're going to now hand over, and the team is going to move into the clean area. And now you're going to see Audra now all ready for the class 10,000 really clean lab where we can do some really amazing science, not just astrobiology, search for dark matter, which you're going to hear about now.
Yeah. So you can see I've changed clothes. It'd be great if I was Wonder Woman and I could just turn around and change, but since I'm not, it takes a minute to get into the clean room suit. So besides using this site as a Mars analog, there's a lot of other exciting science and research going on. So we're going to walk you through into the, and here I am with the director of the Boulby Underground Laboratory. So can you please introduce yourself?
Yeah, well, let's get through here. My name's Sean. I'm the director of the lab, and here we are. So this is our underground laboratory. It's one of just a few underground laboratories in the world for doing deep underground science. And it's class 10,000 as you said,
see.
Why I'm wearing this.
Yeah. So please, can you tell us a little bit about what you do here in this lab?
Yeah, so we do all sorts of science here, from searching for dark matter to geology, geophysics, climate, and now biology and life on Mars studies as well. So some of these projects here are to do with the search for dark matter. Should we go and have a look at that?
Yes, okay. As we're walking over there, can you tell us what dark matter is? It seems like such an abstract concept for so many of us.
So dark matter is just a name that's given to stuff we think the universe is made of. So when you look at the night sky, all the stars and the planets and the atoms that we know about, the stuff that you and me are made of, and the floor, and all the stuff that we know about makes up something like 5% of what's out there.
Only 5?
Only 5. The rest is missing. The reason we think this is when astronomers look at the night sky, things are moving in a way that can only be explained if there's more matter out there than we can see. Galaxies are pulling themselves together too quickly. Galaxies themselves are rotating too fast. All the stars should be flying apart. There seems to be more gravity out there than can be understood if all that is out there is the stuff that we can see.
Okay, so there's a stronger gravitational pull than we can account for.
Yeah, it's almost like there's an invisible hand pulling things up there.
Okay.
And what most astronomers and physicists think is going on is there's matter out there. When I say matter, it's anything that's got weight, anything that's got mass. There's matter out there that we just can't see. So it's dark and it's matter.
Okay, so show us your instrument and tell us how you look for something that we're not really sure what it is.
Right. So this dark matter, we can see, it really does look like this dark matter is out there up in space. But what is it is the question. For a while, people thought maybe it's big things like black holes and stars that we can't see. But now people think, most of the astronomers and physicists think it's particles. So very small subatomic particles that are up in the universe that are passing through the Earth, passing through us right now.
Yeah.
So what we're trying to do with machines like this is called drift here.
Drift.
It's a dark matter detector.
Okay.
What we're doing with this is a particle detector. So it's basically a machine that goes ping whenever a particle hits it. It can be the particles we know about, or it can be dark matter particles.
So any particle would make it go ping.
So with this machine, with these machines, we're looking for pings coming from dark matter. Okay. Now the reason it has to be underground here is if we were to take these machines on the surface of the Earth, anywhere on the surface, they'd be going ping, ping, ping all the time because of background radiation. When you're on the surface of the Earth, you're being swamped by natural radiation. You don't know it, but it's there. Where we're standing now is 1,000,000 times quieter. Because
1,000,000?
Yeah. Wow. Because of all the rock above our heads, it's shielding us. So now these machines are in a better environment to find these pings from dark matter.
So we're being shielded from radiation coming in from the sun.
Yeah.
So that it's much quieter here. There's less particle movement, less radiation, so that we can detect something that has not yet been found.
It's not yet been found, but it's very important because this stuff makes up more than 85% of the matter in the universe, but we haven't found it yet. So there's a race to find it. There's a handful of labs in the world, laboratories, and a handful of experiments looking for it. No one's found it yet, but you know, we're carrying on looking, and we're hoping to find it to prove that theory is true or wrong in the next few years.
Wow. So it's very similar to looking for life on another planet. We haven't found it yet.
Yep.
We think it may be there.
Yeah.
We're not quite sure what it would look like or exactly how to find it.
Yeah, but there's good reason to be looking.
Right.
And so there's reasons why we think it's worth looking. So we go and look for it. Yeah.
Great. Thank you so much.
You're welcome.
So we're going to move now down here where we had some exciting science going on this past week. So as you can see, there's many different stations set up. So as we're walking through, Dr. Sean, will you please tell us a little bit?
There's all sorts of science you can do in a laboratory like this. As you've seen outside there's people interested in life in the rock and the geology and the Mars yard. Inside, there's many different types of science you can do in a low background radiation environment. That we've just passed is a climate-related study. This study here is called Stellar, and Jen here is working on this project. And this is a project to try and understand the effects of radiation or lack of it, very low levels of radiation, which we're in now, the effect of that on microbial life. How do cells react when there's very low levels of radiation?
Right, so if they're used to having radiation on the surface, do they act the same underground where there's much less radiation?
That's right, and you need to go, you can only do that sort of science in an underground lab like this.
Yeah, okay, great. Well, we're here with one of our NASA research scientists, so we're going to pass the microphone off. Thank you very much. Thanks. So we had some very exciting things happen last week here in the Boulby Underground Laboratory, and we have one of NASA's own scientists to tell us all about it. So please go ahead and introduce yourself.
Okay. Hi, I'm Jen Blank, and I'm a research scientist at NASA Ames in Silicon Valley. It's about 2 minutes by car from Google, Google headquarters. And I was part of a group last week who did the deepest sequencing.
Deepest sequencing of DNA. Tell me what that means.
So actually it's with a team from Jet Propulsion Laboratory in Pasadena. And we walked around the lab, walked around some of the tunnels here, and we were collecting samples of soil, which is really ground up salt rock, and any kind of the organic matter or microbes that would slough off people as they walked around. And we tried to look for comparison between different sites, between where there was a lot of people activity and where there was really empty tunnels and there wouldn't be any activity at all, and see if we could find different amounts of microbial material.
Okay, so to see if humans' presence in the mine would make a difference in the amount of microbes in an area.
So how much are we contaminating here?
Okay,
right?
Great.
So we spent a couple days walking around, collecting different samples, and then around the corner there, you can't see it, is we extracted the genetic material from the microbes and then amplified it with an instrument called PCR, and PCR reaction, and then we stuck it in this cool new tool, which is called the MINAR flow cell. It's spelled like Minions, like the movie. but
we kind of look like Minions, so that's
we're like little
appropriate.
Minions, but it's actually MinION, because it's ionic flow cell for being able to have portable capability for sequencing. Usually you have to make the samples and then send them off, and weeks later
Can you show us this instrument?
Yeah.
It looks quite small to be able to sequence DNA.
I don't know if you can see the picture, but here's the blow up of the picture. And it's just here. You just plug it with the USB cable into your computer. And if you take the top off, you can see like this is this little capillary column that pushes the the material around with electronics, and your material has a magnetic signature. And from that, we get counts of how many microbes are there and actually the genetic information from those microbes. So it takes about 2 days to run, and we started it last Thursday. And so we actually, I'm just about to finish. I mean, it's finished over the weekend, and I'm about to open it up. But I just want to show you. So what we do is after we extract the DNA from the microbes, we get a really tiny bit of material, sort of less than a drop. So it's kind of hard to
less
see.
than a drop of material.
Yeah, and that has actually tens and tens of gigabase pairs, which is how big of signature of DNA we
so
have.
It's lots and lots of DNA,
Yeah,
and less than a drop.
And we weren't sure if we'd have enough, if this place would be contaminated enough. Watch me get my glove on. Don't do this at home. Anyway, and then we would take a pipette.
And you're using a glove so you don't contaminate your own cells, correct?
Yes.
With the DNA samples.
I'd be a little more careful and probably wear 2 gloves if I'm working on the bench. So the bench is just a flat surface where we can put all our stuff and try to keep clean. Like we first wipe it down with alcohol, and then we'd protect it with a little chem wipe here.
Okay.
Special towel.
Yeah.
And then let's see, I'll use this one.
So you're putting a tip on the pipette.
Yep. Which pipette? Just a minute. This one. And then I'm just going to show you. So then what you do is you have the pipette will take up liquid, and
so you're drawing up that's the extracted DNA.
Yep.
Okay.
And it's very clear, so it's hard to see. It's probably hard to see on the camera.
Yeah.
And then you would open this lid, and then just very, very carefully put a tiny drop of that material. And again, it's going back to this one.
I see. So it would look like that. Yeah. Put a drop on.
Yeah, and then wait about 48 hours for the counting.
And the DNA would run through some pores, one nucleotide at a time.
And we get, based on what the different microbe signature is with their DNA, we'd be able to tell how much and what types of bacteria are actually around. So that's pretty cool. And this is the deepest anywhere on Earth that this technique has been applied. So we're really excited because 2 things. We had enough biomass, so enough material to sample.
Right.
With just a tiny bit of soil. And we also were able to run this thing with no problem here 1.1 to 1.2 kilometers underground. So we're really excited.
That is exciting. So just to summarize, you took some samples from the surface of the rocks, some samples from the interior of the rock, which is mostly salt, and then you extracted the DNA. So you purified it, extracted the DNA, then you amplified it, which just means to make some copies of the DNA so that there's more of it, so it's easier to detect.
We actually, it's like cooking. There's a little bit of a sort of a flow chart of instructions, and we add different solutions to make the DNA open up, and then target parts of it that we want to reproduce over and over and over again. So we use just different chemistry essentially.
Okay.
On the benchtop, and yeah, so we get enough material to find. But actually, we were not looking in the rocks yet. We are doing that now. We're actually just looking at the fingerprint or the bacteria that was left by people
on the surface.
Yeah, so just our debris and different soils in the rock. So it might be a combination of like bacteria from that's living here normally, and it might be some bacteria from people as we just pollute the environment without meaning to.
Yeah. So you have the DNA sequence, and then the next step is to analyze that. Is it human?
So
is it bacterial?
Stay tuned for next week, and
we'll
be able to tell you. We've also set up little passive air filters around the lab, and actually in the tunnels here, and that's, I don't know if you want to take a look at that. That's the little cross section over there. And the idea is, again, to see what other kind of contamination people are bringing into the lab and into the tunnels in the mine. And in that case, we just have a trap that's just a very, very fine-grained mesh. And we put these little filters here, and it's just capturing passive air. And so we'll leave these out for almost 2 weeks. We may or may not find enough microbes, but it's going to be interesting to compare how many we have from our own system, and our own contamination here versus in air passage in the tunnel.
Right.
So it'll be really cool.
Yeah, so the microbes that are just in the air, is there a difference in the ones in the clean room and in various places throughout?
And in terms of how this relates to planetary exploration, there's something called planetary protection. That it's not that we want to protect Earth from crazy microbes that might attack us. It's what we want to protect the other planets like Mars from any contamination that we clunky humans might bring there.
Yeah, so that's the importance of having a planetary protection department at NASA.
And the cool thing is, I mean, it's good or bad, but we did find enough material here just in our visit to be able to analyze. And so we can develop methods and procedures for protecting the planets in the future.
Great.
Yeah.
Excellent. Thank you so much. I'm gonna grab your microphone. Now, so if you have any questions, don't forget, please leave them in the comments below. We're gonna move now back out into the Mars yard. So I'm gonna be passing this off to Charles Cockle, who is the director of the UK Centre for Astrobiology and the professor of astrobiology at the University of Edinburgh. And so if you have any questions, please put them in the comments below. He's also going to be with Matthias, who is the astronaut with the European Space Agency. So if you have any questions that you would like an astronaut to answer, as he is an astronaut in training, please make sure to put those below. So we'll just slowly make our way out of the clean room, go back past the dark matter detectors. Also, if you have questions about dark matter, I'm sure that the Boulby Underground Laboratory would be happy to answer them. It's a concept that was pretty new to me as well. I mean, I'd heard of dark matter, but I've learned a lot about it this week. It's such a fascinating field of study. So if you're interested in physics, that would be a great thing to go into as well. All right, so this is where the researchers and engineers take a break in the clean room and get some work done in between setting up experiments. So here we are. I'll pass this off.
Thanks a lot.
Yeah, and I will get changed. I'll see you guys on the other side.
Okay, so we're going to go outside now and answer a few questions. And the first person we're going to go and talk to is Matthias Mora, who's an ESA astronaut. So if you follow me out this way, moving back out of the lab again. So we come through here. And as we come through here, I'm going to kidnap an astronaut here. So Matthias, do you want to come and join me out here? Just going to move. Let's have a little interview here. Just wanted to introduce you to Matthias. We're going to be talking more to him on Wednesday about the European Space Agency and how they're linked with our MINAR program, Mine Analog Research. But just a quick couple of questions here, Matthias. So, Matthias, what brings an astronaut underground, a kilometer underground?
Well, when we fly into space, space is an extreme environment. So we need to test all the gear, our procedures, the way we operate. And well, a good place how to practice how to do this in space is like underground. And that's why we're here today, because I want to meet all the scientists, I want to learn from the scientists, and I want to touch all this equipment and instruments and see if we can use this equipment to later on also work on the moon or on Mars.
So you're going to be here for a week, or nearly a week, working with our various instrument teams, testing out drilling, new types of sampling bags, some of the instruments for Mars as well. What do you hope to get out of this week? What are you hoping will happen?
Well, hopefully I will learn a lot, and hopefully I will also get a feel for what is available on, like, in the science community as new instruments, new technology. So to actually push human spaceflight further, because the next step will be to return to the moon, and the moon will be a prep step to fly to Mars.
Exactly. So you can see there that this is not just an excellent environment for testing new instruments and technology, the exploration of space, but also a fantastic place to train astronauts in preparation for future planetary exploration. So thanks a lot, Matthias, and we'll be talking to you more on Wednesday about your goals as an astronaut and maybe some of the extreme environments that you've been to. All right, thanks a lot.
Bye, everyone. Enjoy, yeah?
So we've had some questions from students from the Callum Centre who have sent in some questions. We're really proud of our link with the Callum Centre in India. Callum was one of the founders of the Indian space program, often thought of as the father of the Indian space program. And it's very inspiring. And you will have noticed already that we have a number of people here who have connections with India, the group from Luleå in Sweden, also the group working on Raman, connections with the very ambitious and successful space program in India. So we plan to continue our connection with Callum, but some questions that have been sent over to us. First of all, what's it like to be an astrobiologist is one question. Well, being an astrobiologist is really exciting. Astrobiology is a very broad term, and it basically covers the study of the origin of life, how life developed on the Earth over 3.5 billion years ago, and how it's persisted on the planet, and whether we might find life elsewhere. Is there any other life elsewhere in the universe? One of the biggest questions in science. Astrobiology takes scientists to all sorts of different environments, particularly extreme environments. So here we are at Kilometer Underground. Many of the people who are here in these 2 weeks of our analog program have been to Antarctica. They've also been to the Arctic, other volcanoes, asteroid craters, and in some other deep subsurface environments as well. So astrobiology is very exciting. It's intellectually very exciting. It takes you into science. It takes you into technology development. And as we've just seen with Matthias, it also takes you into the realms of the human exploration of space, bringing you into contact with explorers elsewhere. Another question that the Callum Center asked, a very interesting question, is there any link between science and spirituality? What is the connection between science and spirituality? Very, very intriguing question. It's a very important characteristic of a scientist to try and be objective in all the things that we try and study. Whether you believe there's some higher purpose to humanity beyond the purpose we set for ourselves is really a personal matter. But what we're interested in as scientists is really getting to know the reality of the world as best as we can through experimentation, through repeating experiments and observations. So certainly there's no inconsistency between people having spiritual interests, but science is very much about the use of the scientific method. There's no such thing really as science. It's just a method of understanding the universe around us.
We have a question, live question
coming in.
Colin Center. How do we know that if we find life outside Earth, it will be safe for humans to interact?
It's a very good question. Live question from the Callum Center. How do we know that if we find life outside of the Earth, it will be safe for humans to interact? That's a fantastic question. People think about this, and it's covered by a field called planetary protection. And these are people in space agencies that think about what would happen if we contaminated another planet with life from our own planet, and what would happen if we brought back life to Earth that turned out to be dangerous to the Earth. That may be a very unlikely thing, but it's still something we all want to think about, just because we want to be prudent and careful in the way in which we explore space. So it's a very good question, and that means that scientists need to go and get samples of life if we would ever find life elsewhere. They would have to analyze it, probably in very strict quarantine conditions on the Earth, to make sure we were happy that it was safe before we started distributing it to other laboratories. So that's a very, very good question.
Okay. We also have a question from Vicky Craig from Baku, Azerbaijan. And this has been explained, but maybe give a little more detail. Why underground and not above?
Yeah, a question from Vicky in Baku in Azerbaijan. Why are we here 1 kilometer underground and not on the surface? Well, a couple of reasons. First of all, this is a working mine. And miners are very interested in developing small, reliable instruments that can be used in mining environments to study the ores or the rocks that they want to mine. And that's exactly what planetary scientists want to do, develop small, reliable instruments that can work in extreme environments. So we have a direct working relationship here with a working mine, which is very interesting. The second reason we want to do that is because when we go to places like the Moon and Mars, explorers will probably want to be underground, or at least to explore underground, where on Mars they might get access to environments that are more habitable than the radiation-soaked surface. And eventually human explorers might even want to build settlements below the surface of the Earth, where they're protected from below the surface of Mars, and where they're protected from surface conditions. So the idea of coming here below the surface of the Earth, a kilometer underground, is to learn how we might explore lava tubes and caves on the Moon and Mars, and maybe even build settlements underground on those planetary bodies where people are protected from the extreme conditions on the surface.
Great. We got another live question from the Colin Center from a 13-year-old in Lucknow. What course should I take if I want to walk on Mars when I grow up?
Great question. question from a 13-year-old in Lucknow in India. Thank you, from the Cullum Center. What course should I take if I eventually want to walk on Mars? Well, the great news for you, age 13, is that there is an ever-increasing amount of space exploration going on around the world, not just from national governments like the Indian government, but also private space exploration as well. So you may have a much better chance of getting to Mars than older people like me. What course should you take? I'd really recommend doing a science course, but it's not essential. It could be that even in the future, artists will go to Mars. But for the meantime, most of the people that go into space have some sort of science or engineering background. So I'd really recommend, if science interests you, going into biology or physics or chemistry, getting a really good science degree, work hard at school, that's really essential, do all your homework, and eventually then you can go on to college and prepare yourself to be a scientist that could go to Mars. And as I say, you're 13, you've got plenty of time ahead of you. In 20 or 30 years from now, it might be quite easy to get into space, at least into Earth orbit, with private corporations, and eventually go on to Mars. So my basic recommendation to you is stay enthusiastic, stick with the dream, pursue your interests, and eventually you will get to Mars.
I'm going to grab the microphone from you. So we have a question from Daniel Ricardo. What do you think is the most important factor to measure using the rovers for looking for life on Mars?
Yeah, that's a great question. What's the most important factor to measure in looking for life using rovers? Well, actually, there's no single thing to measure. You need to measure lots of things. So you need to understand whether there were conditions that could have been habitable, could have been good for life in that environment. That means looking for the history of liquid water. We want to find rocks that show evidence that there was lots of water there where life could have survived. We also want to find elements that could be useful for life, like nitrogen and phosphorus. So we need to look at the geology of the rocks and their geochemistry. What are they made of? And then the next step is that you really want to get one of those samples and see if you can actually find the signatures of life, the direct signatures of life, maybe even fossils of life. That means sending a sophisticated rover to look in those rocks, or perhaps bringing samples back to the Earth so people can look at those rocks in laboratories here where they have more sophisticated equipment.
Excellent. Okay, we have a question, another question from the Collins Center. Why have we not sent someone to the moon in so many years, and why haven't women been to the moon?
So another question from the Callum Center. Why haven't we sent anyone to the moon for so long, and why haven't women been to the moon? Well, the answer to both of those questions is that national space programs really backed off from going to the moon after the Apollo program. Astronauts successfully went to the moon, and then people just felt they had been there and they didn't need to go back. And that, I think, is a great disappointment to most of us who were born at around that time and shared the vision of space exploration. As more private corporations go into space, hopefully there will be new missions to the moon. And of course, now, hopefully at this time, we'll see men and women going in equal numbers to the surface of the moon as astronauts and exploring the moon once again.
Great. We have another question from India. What is the importance of cryogenics in relation with astrobiology?
What is the importance of cryogenics? Well, that's an interesting question. Many astrobiologists study life in extreme cold environments like Antarctica or the Arctic. In fact, if you look at most of the planets in the universe, or at least in our solar system, where we might think there are habitable conditions, they're generally cold. Places like Mars, average temperature of -60, although it can obviously get warmer. The icy moons of Jupiter, like Europa, and the icy moons of Saturn, like Enceladus. Almost everywhere you look, places where there might be life are generally colder than the Earth. So understanding life and conditions at low temperature is really an essential part of astrobiology. So the connection between cryogenics and astrobiology is that most of the astrobiologically interesting places in the universe are cold.
Okay, we have some other questions here from the Collins Center. Is there ocean beyond Earth, and how, if there is, how are these different from the ones on Earth?
Yeah, great question from the Callum Center. Are there oceans beyond the Earth? And there's growing evidence for many oceans beyond the Earth. We know of an ocean beneath the surface of Jupiter's moon, Europa, that has as much water, some people estimate, 2 times as much water as all of the Earth's oceans combined on that single moon. Of course, the moon is a lot smaller than the Earth, but the ocean is very deep, so lots of water. Look outwards to Saturn and you find Enceladus, a small moon about 500 kilometers in diameter, and it too contains liquid water beneath its surface. And people are even talking about the possibility of a subsurface ocean on Pluto.
Wow,
Go
really?
to the furthest distances of the solar system, and you might find liquid water. So everywhere we look, people are finding evidence of water underneath the surface of icy moons. Do they have life in them? Of course, we don't know, but that shows that we have a lot to do in astrobiology, which is to explore these places. So many astrobiologists and instrument developers, including some of the people here in MINAR, are interested in going to these icy moons and exploring them for life.
So as an astrobiologist, why is it important for you to look in places where there's liquid water? What's the significance of liquid water?
Yeah, so if you build a life form, a replicating life form, you need some sort of liquid in which to do chemical reactions. If you can imagine drying something down on a table, when something's dried down, the molecules can't move around very easily. They just sit there and do nothing. But in a liquid, things can move around. It's a bit like if you add food coloring or bubble bath to water, it spreads through the water. Water provides a liquid in which chemical reactions can occur.
Okay.
And every life form on the Earth requires liquid water to do its chemistry. There have been some tantalizing, interesting suggestions of liquid ammonia, even sulfuric acid as alternative liquids for life. But so far, there's no evidence for that. We think liquid water is at least what we know to be essential to the life on our own planet. So when we go elsewhere, that's what we're looking for. Liquid water as at least one requirement for the presence of life elsewhere.
Okay, so backtracking a little bit, you are an astrobiologist. Can you give me a definition of astrobiology? What does that term mean?
Yeah, I mean, the definition is, well, one NASA definition is the origin, evolution, and distribution of life in the universe, or as I like to tell my students at Edinburgh, life, the universe, and everything. I think if I was to summarize astrobiology, I would say it's the connection between biological sciences and space sciences and astrophysics. Why is it that this planet has lumps of self-replicating organic matter that we call life scattered around on its surface and just beneath the surface? What is this phenomenon of life with a code, and could we find it elsewhere? So that's one of the questions of astrobiology.
So if someone wants to be an astrobiologist, do we have a question?
Yes, and it's kind of relates to what we do.
Got another question?
The existence of extraterrestrials hogs.
Extraterrestrials on Earth.
Is the existence of extraterrestrials a hoax?
Oh, is the existence of extraterrestrials a hoax? We have no unequivocal, certain evidence of extraterrestrial life. Not a single cell has yet been discovered that we can say with certainty is extraterrestrial life. That's the reality of where science is at the moment. Many people like to believe they've found extraterrestrial life. Some people go even further and think they've had contact with extraterrestrial life. But there is not one single scientific paper that is agreed by multiple science groups that is evidence for extraterrestrial life. So we very much are still at the forefront of answering that question, and we still require an answer to this question: are we alone in the universe? At the moment, we do not have an answer to that question.
Great. Well, I think, we have another question. Okay. So we have a question. Do you expect the rocks on Mars to be like the rocks you are studying in the mine? And this is from her student, Alex.
Yeah. Do we expect the rocks on Mars to be similar to the rocks we're studying on Mars? Very good question. Yes. There is much evidence for salts on Mars. Here down in Boulby, we find salts made of chloride, like your table salt, sodium chloride. We know that there are chlorides on Mars. We also find salts made of sulfates with sulfur in. A lot of sulfate salts down here in the mine. We also know there are sulfates on Mars. One thing we don't find in this mine is basalt, volcanic rock, which is what the rest of Mars is made from. But some of the most interesting environments on Mars are environments with salts in, because salts generally accumulate where water has evaporated. So we find salts in craters on Mars where the water has evaporated and we get the salts left behind in a crater. So salts can be indicative of liquid water environments, places for life. So down here in Boulby, we're looking at all these varieties of salts, the chlorides and the sulfates, and looking at how well they preserve life with people from NASA, JPL, and places in Europe as well, looking at these different salts. We're looking for these biosignatures of life, these signs of life in the salts. So in one sense, it's very different from Mars, but in another sense, it has a very interesting parallel with Mars in the study of salty environments, water-rich environments that can be of interest to understand both the geology and the potential habitability of that planet.
Great. We have one more question, so we have time to answer one more.
What have you discovered that would be useful for the future of astrobiology?
What have we discovered that will be useful for the future of astrobiology?
Well, where do I start with that? We don't have much time. Let me try and give you some basic examples. We've learned a lot about science. What sort of microbes live deep underground? What sort of microbes live in brines down here? So we have a PhD student who's just finished his PhD looking at how the different brines influence the microbes down here. So we learn a lot about science. We've learned a lot about the sorts of organic signatures of life, ancient signatures of life that are preserved in salt. And then it's not just about science, it's also about technology. We're testing all these instruments, from life detection instruments to drills. That's taught us a huge amount about how to build instruments for other planets and to do astrobiology on other planetary bodies. And then finally, what have we learned that's useful for society here on Earth, which is another part. It's not just about looking for life elsewhere. We're working with miners in Boulby Mine. There's an active working mine, the deepest mine in Europe, 1,000 kilometers of roadways through this mine underneath the North Sea where they're mining salt. And we're working actively with the geologists and the people here at the mine to develop and test instruments that could be used in a mining environment. So one of the instruments that was tested here a couple of years ago is now being used to work with metallurgy companies to look for metal ores deep underground. So some of the technology tested in this mine doesn't necessarily end up in this mine. It can be used by other mining environments as well. So how do we improve our ability to extract resources from the Earth as those ores, as those resources become more depleted? How can we do it more inefficiently and less wastefully? Developing miniature instrumentation that can be used in a mine can be of enormous interest to the mining community. So from the science of looking for life on Mars to developing instrumentation for future missions and improving our ability to mine ores on the Earth responsibly and efficiently in the future. The Mine Analog Research Program here covers all of these areas and contributes to generally the advance of astrobiology and its applications on Earth and beyond.
Great. Okay, I think we're out of time. If you have future questions or any questions you would like us to answer in the future, put them in the comments below. You can also send them to #UndergroundAstrobiology. We have 2 more live links that we'll be doing on Wednesday at 10 o'clock British Standard Time and 3 o'clock British Standard Time. So feel free to join us.
And remember that Matthias Mora, the astronaut,
Yes.
will be back here on Wednesday. If you want to talk to an astronaut, ask him some questions about what he's doing down here, what he plans to do when he eventually gets to Mars. Wednesday is your opportunity.
Yeah, Wednesday we will focus a lot on the astronaut and his astronaut training. So be sure and send us your questions.
Bye-bye.
Thanks for joining, guys.